Climate engineering. Contour trenching. Forest destruction compacts vast tracts of the world's land surface, rendering it impenetrable to rainwater infiltration. Trenches excavated along selected contours restore the soil's infiltration capacity, thereby renovating underground water storage. These year-round accessible subsurface volumes ensure the re-emergence of grasses, shrubs and trees. Contour trenches can be excavated by hand or machine, making it affordable for all walks of life above poverty level. Intense land use furnishes sufficient manual labour, whereas sparsely populated regions are easily treated with earth-moving equipment. The first rains infiltrate the rehabilitated land and saturate underground, reviving biodiversity, however dormant. The initiated evergreen cycle of the treated earth has thereby started in earnest. The same rainfall in torrential discharge rips non-contour trenched land apart, through erosion followed by landslides. On the other hand, a more pacified and evenly distributed rainfall has the same devastating effect. These opposite rainfall patterns bring death and destruction on non-contour trenched land. Both patterns have an uninterrupted, life-generating impact on contour trenched earth. So what makes water, which is the condition for life, so lethal outside these treated boundaries? Creating water for human consumption. Water is fundamentally lazy and always in search of the easiest and fastest flow in order to go and lie dormant. It will flow to the surface at the last trench and proceed as surface water to the easiest accessible lower destination. Before it reaches the surface, the water flow can be transferred as consumable water in a piped conduit. The more this contour trench system is expanded in altitude, the greater the pressure of drought-resistant, year-round water which can be achieved. Creating year-round water for animals and plants. Wasteland with 100 millimeters of annual rainfall receives 100 million liters of water per square kilometer per year. That water volume is sufficient to turn desert land into forested grassland, and to provide 20 liters of water per day to 1,600 head of cattle, and 300 liters of consumable water to 440 people every day of the year. Excess water pushed onto the land surface can be recycled into an evaporation-free underground flow. A horizontal stone wall construction disperses the concentric surface flow towards the next contour trench formation. In this way, accumulative surface water sources can be established wherever and whenever desired. 200 square kilometers of forested grassland increases local rainfall by 20%. River water dispersal into subsurface infiltration. When surface runoff water drills deeper into the land, the time has come to divert that water into a productive flow pattern. These seasonal rivers have the tendency to sink even deeper, thereby draining both runoff rainwater and groundwater. The land starts to leak to the point of finally drying out, except for some deep-rooted trees and superficial seasonal vegetation. A low dispersal wall at the beginning of the riverbed diverts shallow, silt-poor river flows into the contour trench unit. Downstream, a higher wall in the eroded riverbed centralizes torrential, mud-filled river water back into its original stream pattern. Stone walls at the higher side of the contour trenches filter and distribute the diverted river water into an overland sheet flow. These waters then infiltrate into the soils to become an underground and cool, clean flow into the dam. In the course of the rain season, the rejuvenated vegetation cover turns into the natural filter and distributor of future river water. The undercurrent turns into evaporation-free storage and coolant of the dam's surface water once the rains have ceased. As a result, the dam becomes a year-round surface water point if consumption does not exceed subsurface infiltration. Returning Kilimanjaro's glaciers. Forest destruction in the Kilimanjaro region left Africa's highest mountain as a lone and incontinent giant. Twice a year, heavy rainstorms from the Indian Ocean enter the mountain's hemisphere. These saturated rain clouds torrentially discharge when forced towards higher and therefore cooler altitudes by the mountain elevation. Unable to accommodate this instant local water increase, these volumes quickly and therefore destructively discharge towards surrounding land depressions. Once settled there, they evaporate during the dry season in the heat of the scorching sun. These cloud formations disappear beyond the horizon, enhancing further flood risk in the west. A doubling of the Kilimanjaro forest through the construction of water dispersal and infiltration units preempts rainstorms through more evenly distributed rainfall. They achieve this through extended forest humidification and subsequent cooling. The remaining lighter rain clouds are propelled by wind elevation towards the summit. A further growth of the glacier is generated by increased forest evaporation, responsible for rainfall extension into the dry season. Urban water, food and energy production in Bamako, Mali.